So now I want to go over some quantum field theory, or more generally classical field theory. I'm going to kind of bunch this into sort of one video, and we're going to go over the Lagrangian. Now, if you don't know what the Lagrangian is, then you might be at a disadvantage for this video. I'm going to assume you know quite a few things, like some calculus. So I'm going to go over this. So I'm going to just say that this is the derivation of the Euler-Lagrange equations. Euler-Lagrange equations. And I am going to assume that you know some calculus. And that is actually pretty much it. So maybe you actually will be able to understand a lot of this. I'm going to attack the Lagrangian in a way that's a little bit different than what most people what most professors and what most people will tell you. So without further ado, let's get right into this. Of course, I have to promote myself a little bit here. If you enjoy these type of lectures, please go onto my Patreon page, and I'm going to be trying to crank out as many of these lectures as I possibly can. Sometimes you'll see me down here when I have the time to do it. Oftentimes I'm in the lab and I can't put myself in there, but when I can't, I'm just doing it like this. You can go onto my Patreon page and you can recommend that I do some practice problems so that you can have a better understanding of what you're getting into if you're studying this kind of stuff. Anything from general physics to general chemistry, quantum field theory, quantum physics, classical mechanics, just anything you could possibly name. I really, really enjoy doing this kind of stuff. I've been studying it for a really long time. Let's get right into this. So, we want to define a variable. Let's call it A. Okay, we're going to call this the action of a system. And the action of a system is defined like this: the integral between time 1 and time 2 with respect to time of something called the Lagrangian. Okay, now the Lagrangian is a function of what? The Lagrangian is a function of r. These are just some dummy variables. Perhaps we have a radius to take into account into our system. Perhaps we have an angle 1 in our systems. Perhaps we have another angle in our system. Okay, and then perhaps we have an azimuthal angle in our system as well. Okay, so these are all the independent variables in our system. So this could be almost like some Atwood machine that also has some azimuthal component to it. Okay, so we have like something that's swinging like this, where from a roof, where this is angle 1, this is angle 2. Okay, and then this thing is also turning around like this, and this angle here is our azimuthal angle, so it's turning around at us, almost going like this. Okay, so we have 3 independent variables, and then we would also need to have 2 radiuses. So say we'll have radius 2 here as well, because we have this radius and this radius here. All right, so it's a function of all these, but it's also a function of the derivative of all of these. So all of these independent variables here, that's an R2, have derivatives to them. So there's R1, R2 and its derivative, theta 1 and its derivative, and so on. So the Lagrangian of this entire system has all of these independent variables in them, and we boil this down to this. This will be boiled down to something that looks like this: T1, T2, dt Lagrangian, and we call this qi and qi dot. Okay, and this is our action. So what are the q's? The q's just so whatever value of I we have in here, so say q1 is equal to r1, q2 is our second independent variable is r2, q3 could be our first angle, q4 is our second angle, and q5 is as a mutual angle, something like that. So this all boils down to this. Okay, so now let's take the derivative of a with respect to a parameter little a. Okay, now what is this little a? Well, all of these are independent variables. Yes, that's true. But r1 could be different. R1 could be a function of a. Okay. In other words, R1 might be different for from some different perspectives. As to say we're measuring, say R1 is 4 centimeters, and our A here will tell us, are we measuring in centimeters, are we measuring in meters, or something like that. So we have, this is almost like a basis. So the action, and I also want to explain here that the integral over all times here, over all times, implies that R1 is not just a function of some parameter. We have to define some parameter by which R1 is defined, but it's also a function of time. Okay, so again, a way you can imagine this is that we have some line here of the real numbers, okay, and here's 0, and here's our value of a. Okay, we take this and we put it into this function here. Okay, we put it into here and we get a value for R1. Okay, so say a was 1, right? If a was 1, we put that into here, and R could be 1 if a is 1. R could be 2 if a is 2. Okay, you can also think of this as you can also think of this as, this is the A domain, this is the R1 domain, and here's 0. Here is where here's R of A1, or here, actually I'll write it like this. And this here, map R1 of A maps us onto 2, for example. So we want to pick just some ordinary line, okay, of the real numbers, and R1 is going to take in this value of A and spit out a value for R1, okay? So this is almost like the basis of the basis. This is the real numbers, okay? And R1 is a function of the real numbers because, again, R1 has some value to it, okay? And we want to take the derivative of the action with respect to this basis here. And what do we get? We get that T1 to T2 dt. So the first thing we want to do is take the derivative of the Lagrangian. So the derivative of the Lagrangian with respect to Q1, or Qi, I'll just say Qi. Okay, remember this is multiple equations here because I has multiple values like we set up here. Q1 times the derivative of Qi, this is I said 1 there, with respect to A, so dA, okay? And then we also have, I'm going to erase a little bit of stuff here to give myself some space. And then we have the derivative of the Lagrangian here with respect to its second independent variable, which is the derivatives of each independent variable here. So to keep in mind that we have, these are all the positions, so these are all positions, if you will, and these are all velocities, or the rates of change of these independent variables. So velocities, if you will. Okay, and then we have dqi dot with respect to alpha, or a. So what can we do with this now? We could say that this is equal to the integral over t1 to t2 dt. This stays the same, so dl dqi dA minus dl dqi, and this is just the time derivative. This is just a time derivative, so I'll take the time derivative out, dqi dA. All right, that's not too difficult to conceptualize. This is a time derivative, so I'm just taking the time derivative out and I'm putting here. This we could say is a constant, so we can just rearrange this a little bit more. T1 to T2, we're integrating over all of time, dt, and we get the derivative of the Lagrangian with respect to qi, the derivative of the qi dots, or qi with respect to alpha, or a, okay? And I'm just going to take this time derivative out here, dqi dot, and then that is a dqi over dA. Now you can see here, what I failed to mention is that, okay, we took the derivative of this, and the proposition, this is the proposition is that this equals 0, that the derivative of the action with respect to this, with respect to the real numbers here, with respect to the actual basis of everything, is equal to 0. Okay, and so we're saying that this is equal to 0. Okay, so so what we have now is we're almost there. We're almost there. We have T2 and T1 dt. Okay, and what we have here is dl dqi minus dt dl dqi dot dqi dA. I just factored this out because it's common in both of these. So I factor that out and we say that that equals 0. Okay. We have come now to the Euler-Lagrange equations. Okay, equations of motion. And what we have is, so this here, the derivative of our independent variables with respect to how we're measuring them is, this could be 0, but this is almost always never going to be 0, okay? This is almost always never going to be 0 because as we change, because this here will always change with respect to the coordinate that we're measuring with. Okay, no matter what value we pick here, there's always going to be some value for r. In other words, okay, it's always going to change. It's always going to change. It's going to go. In other words, this value here is always, R1 is always going to have a value anywhere we go. It could be 1, it could be 3 for some value of a. Okay. If this wasn't to change, if R1 stays 2 for 2 values here, so say this is a 2, and both of these values map onto 2, then we might have some problems. Okay. But that's what this means. That's what this means. We're saying almost by definition that this is almost, this is not 0. So this here has to be 0. Okay. So in other words, dl dqi minus d dt, the time derivative of my Lagrangian with respect to qi dot is equal to 0. This is my Euler-Lagrange equation. This is the Euler-Lagrange equation. Equations of motion. Right here. This is my Euler-Lagrange equations of motion. Okay. So this is a very, very important equation. And what I'm going to do here is I'm going to provide you a visual representation or a visual understanding of this equation first. And then I'm going to go into promoting this into a form suitable for quantum field theory. Okay? So imagine our Lagrangian it's almost like this thing at time equals 1, at t equals 1, that contains all of our independent variables within the system. So in this case, we had, so I'll draw this out. We have this object here. It's like this mathematical object that contains all of our independent variables here. Oops, my bad. All of our independent variables here. We have R1, we have R2, we have theta 1, theta 2, and our azimuthal. And all of these, we have to measure these somehow, right? We have to measure these somehow. And that's what this real axis is. Okay, so it's a function of A, but also a function of time. Okay, because this value, we have to measure this somehow, and that's what this A tells us. But at some period in time, this thing might also change. And this is alluding, again, to a quantum field theory. Okay? And same thing goes for all of these. Okay, so we have A and T. We have A and T. These are all functions of A and T. All right. Some of these won't change with respect to time, but they will change with respect to how we measure them. Okay? And so at time equals 2, or time equals 2, this thing will change. The Lagrangian will change. Okay? But at time equals, so say this thing evolves at time equals 2, or let's say time equals 2, and our Lagrangian might change. Because, so say it takes on a different shape or a different form, it still has all our independent variables in it. R1, it has R2, has theta 1, and so on. Okay, it has all our independent variables. But because these things are different values now at a different time, our Lagrangian is going to have a different shape to it, and then our Lagrangian might look something like this at Lagrangian at t equals 3. This is just like a very abstract representation. We still have all of our independent variables in here, okay, and so on. We still have all of our independent variables in here, but the difference here now is that as we go through time, each one of these values might change a little bit, changing the overall structure of the Lagrangian, okay? And there might also be some connectedness between, so this might be connected, so these might be connected, there might be connections between these, there might be connections between that, there might be connections between that and these guys. So all of these are connected, but if one of these values were to change at some different time, then the Lagrangian will also change its structure. Okay, this is how I sort of go about visualizing what a Lagrangian is in a very abstract way, but it still helps me organize my thoughts when it comes to this kind of stuff. Because again, when we get into quantum field theory, being able to abstract things is going to be very, very, very useful. Okay, so how do we allude now to a quantum field theory? So we have our Euler-Lagrange equations here. What I'm going to do here for quantum field theory is I'm going to say that the Lagrangian now is a function of not q, but phi of I, okay? d dt d phi I, and its derivative equals 0. And you might think, okay, what on earth did you just do? I literally just replaced symbol with symbol, q with phi, okay? But this is actually important because phi, q's are coordinates. Q's are coordinates. Phi is a field. Q's are coordinates, phi's are fields. Okay, so that means associated with our R1, we have an R1 field. Okay, now this is why doing something like this is so important to understand. Doing something like it's a function of A and T. This here now is a function of A. This is a function of A and T, just like we've been saying. But here, in this sense, A is usually almost always fixed. Okay? And T is really the only thing that's changing. Okay? What we're saying here is that we're really, really acknowledging this A value here. And we're saying that if we have some space now, we have some space, R will take a different value in space. So we have some space. So here's X. So here's some value. So here's a spatial coordinate. And R1 has some value here. R1 will have might have a different value right here. Okay. So this is where the quantum field theory. So this is the Euler-Lagrange equation for quantum field theory, or for fields more generally. Is that each independent variable is spread over time and space. Okay. And depending on where it is in space, or where we're observing in space, this independent variable will have a certain value. And that's what that's sort of what takes into account this value of A. Okay. So again, this is the Euler-Lagrange equations this is for classical field theory. This is for classical field theory, and this is for quantum field theory. Okay. Okay, so the field theory again. So the field theory takes into account this possibility right here, where our independent variables can have different values at different locations in space and time, making them fields. And that is our promotion to field theories and quantum field theories. Okay? And so in this, we went over a lot. It's been 25 minutes. We went over a lot. We went over the Lagrangian and we promoted it to a field theory. Okay? But hopefully with this understanding, we'll be able to now go into some more example problems in quantum field theory and even in classical field theory. Okay? So I hope this all made sense. Again, if you like this kind of topic, if you like this kind of this style of teaching, you can go onto my Patreon page and you can request for some specific example problems, or you can go ahead and just keep on watching as I produce more content. And I hope to see you in the next one. Thanks.